you are time traveling right now, not in some science fiction sense, not metaphorically. You are literally moving through time at 1 second per second. And that movement is governed by the same physics that would allow you to travel to the past or future. The difference between what you're doing right now and what we call time travel is not fundamental. It's just a matter of degree. I'm Leonard Susskind, and I've spent 50 years thinking about space-time relativity and the nature of temporal reality. And I can tell you something that will fundamentally change how you think about time. Time travel isn't some exotic phenomenon waiting to be discovered. It's happening everywhere, all the time, including right now as you watch this video. The universe is full of time travelers. You just don't recognize them because they don't match your science fiction expectations. Every GPS satellite orbiting Earth is a time machine. Every particle accelerator is creating particles that travel to our future. Every massive object in the universe is warping time around itself, creating regions where time moves at different rates. Time travel is not only possible, it's mandatory, it's built into the fabric of space-time itself. The universe cannot exist without it. But here's what disturbs me most about our understanding of time travel. We think of it as traveling to a specific time, like going to the year 2087 or returning to 1955. But that's not how time actually works. Time is not a river flowing in one direction. Time is not a timeline with past, present, and future lined up like beads on a string. Time is something far stranger, far more flexible, and far more disturbing than most people imagine. Time is relative. What Einstein showed us in 1905 is that there is no universal clock, no cosmic timekeeper that ticks the same for everyone. Your time and my time are different if we're moving relative to each other. And that difference isn't just theoretical, it's measurable, it's real, and it's happening right now. Let me give you the simplest example of time travel that's occurring at this very moment. There are cosmic ray particles, ones created high in Earth's atmosphere by cosmic radiation that shouldn't be able to reach the ground. These particles have a very short lifetime. They decay in about 2 microseconds. At the speed they're traveling, they should disintegrate long before they reach sea level. But they don't. They arrive at ground-based detectors in large numbers, and we can measure them directly. How is this possible? Time dilation. From our perspective on the ground, these muons are traveling so fast that time slows down for them. Their internal clocks run slower. What should be a 2 microsecond lifetime stretches out to much longer, giving them time to reach the ground before decaying. But here's the key insight. From the muon's perspective, it's not experiencing slow time. From the muon's reference frame, its lifetime is still 2 microseconds. Instead, the distance to the ground has contracted due to length contraction, another consequence of special relativity. Both descriptions are correct. Both are happening simultaneously. The muon is traveling through time and space in a way that defies our everyday intuition, and this is occurring millions of times every second all around you. These particles are time travelers, arriving in our present from their past, and they're doing it through the fundamental mechanics of space-time. But cosmic ray muons are just the beginning. Let me tell you about something even more dramatic. GPS satellites. The global positioning system that tells your phone where you are depends absolutely on time travel effects. Without accounting for time dilation, GPS would be off by miles within hours of operation. Here's how it works. GPS satellites orbit Earth at about 12,500 miles altitude, moving at roughly 8,700 miles per hour. At this speed and altitude, several relativistic effects come into play. Special relativity tells us that moving clocks run slow. From our perspective on Earth, the clocks on GPS satellites should tick slower than Earth-based clocks because they're moving faster than we are. But general relativity tells us that clocks in weaker gravitational fields run faster. The satellites are farther from Earth's gravitational well, so their clocks should tick faster than ours. The general relativistic effect is larger than the special relativistic effect, so the net result is that satellite clocks run about 38 microseconds per day faster than Earth clocks. That might not sound like much, but GPS depends on incredibly precise timing. The system works by measuring the time it takes radio signals to travel from satellites to receivers. Light travels very fast, about 1 foot per nanosecond. A timing error of 38 microseconds per day would translate to position errors of about 6 miles per day. So GPS satellites are continuously adjusted to account for the fact that they're experiencing time at a different rate than we are on Earth's surface. Every GPS satellite is a time machine, and every time you use GPS navigation, you're benefiting from our understanding of time travel. Your phone can tell you where you are because engineers accounted for the fact that time passes differently at different locations in space-time. This isn't just a technical curiosity. This is reality. Time travel is so fundamental to how the universe works that our most basic technologies depend on it. Without time travel effects, GPS wouldn't work. Without time travel effects, particle accelerators wouldn't work. Without time travel effects, the sun wouldn't shine the way it does. But here's where things get really interesting and really disturbing. If time travel to the future is not only possible but mandatory, what about time travel to the past? Can we go backward in time? And if we can, what does that mean for everything we think we know about cause and effect? The answer is complicated, and it should make you uncomfortable. General relativity, Einstein's theory of gravity and space-time, allows for solutions that include closed time-like curves. These are paths through space-time that loop back on themselves, allowing an object to travel to its own past. Not all solutions to Einstein's equations include these curves, but some do, and that's deeply troubling. The most famous example is the Gödel solution, discovered by the mathematician Kurt Gödel in 1949. Gödel showed that if the universe as a whole is rotating, then there exist paths through space-time that allow travel to the past. The entire universe becomes a time machine. In Gödel's universe, you could, in principle, travel in a large loop through space and arrive back at Earth before you left. Gödel's solution doesn't describe our actual universe. Our universe is expanding, not rotating in the way his solution requires. But the fact that Einstein's equations permit such solutions at all is disturbing. It suggests that the prohibition against traveling to the past is not fundamental to the structure of space-time. It's contingent on the specific conditions of our universe. There are other examples. Rotating black holes, called Kerr black holes, can under certain circumstances create closed time-like curves in their vicinity. Traversable wormholes, if they exist, could potentially be turned into time machines. Cosmic strings, hypothetical one-dimensional defects in space-time, could create situations where time travel to the past becomes possible. None of these scenarios are simple. None of them are easy to achieve. All of them require exotic conditions, enormous energies, or forms of matter that may not exist. But the point is that the laws of physics, as we understand them, do not absolutely forbid travel to the past. They make it difficult, perhaps impossible with any foreseeable technology, but not fundamentally impossible. And this creates profound paradoxes. If you can travel to the past, can you change it? Can you prevent your own birth? Can you kill your grandfather before he meets your grandmother? These are not just logical puzzles. They're questions about the fundamental nature of causality, free will, and the structure of reality. Most physicists believe that something must prevent these paradoxes. Stephen Hawking proposed what he called the chronology protection conjecture. The idea is that the laws of physics conspire to prevent the formation of closed time-like curves that could lead to paradoxes. Maybe quantum effects destroy any time machine before it can be used. Maybe the universe has some built-in mechanism that preserves causality, but we don't know. We don't have a complete theory of quantum gravity that could tell us definitively whether time travel to the past is possible. We're making educated guesses based on incomplete theories. And the fact that we're even having this conversation tells you something important about the nature of time. It's not what you think it is. Here's something that will really disturb you. The time travel that's happening right now, the time dilation effects in GPS satellites, the cosmic ray muons reaching Earth's surface, all of this is creating a situation where simultaneity breaks down. Events that are simultaneous for one observer are not simultaneous for another observer moving at a different velocity. Think about what this means. Right now, at this moment, there are events happening on distant planets that you would consider to be occurring now. But an observer moving at high speed relative to you would consider those same events to be in the past or future. There is no universal now. There is no moment that is the present for the entire universe. This is not a matter of measurement error or technological limitation. This is fundamental to the structure of space-time. The present moment is not a universal slice through the universe. It's a local observer-dependent concept. What exists now depends on who's asking the question and how they're moving through space-time, and this has implications that go far beyond physics. If simultaneity is relative, then the very concept of causation becomes problematic. How can we say that event A causes event B if different observers disagree about which event happened first? How can we maintain our intuitive understanding of cause and effect when the temporal ordering of events depends on the observer's motion? The answer is that we can't. Our everyday understanding of time, causality, and reality is fundamentally wrong. It works for slow speeds and weak gravitational fields, the conditions under which human intuition evolved. Breaks down when we consider the universe as it actually is, not as it appears to us from our limited perspective. Let me tell you about another form of time travel that's happening right now, and this one involves you directly. Every time you accelerate, you're changing your rate of passage through time. When you're in a car that speeds up, when you're in an elevator that starts moving, when you're on an airplane taking off, you're experiencing time dilation effects. These effects are tiny at the speeds and accelerations we encounter in everyday life, but they're real and measurable with sufficiently precise instruments. Atomic clocks can detect the time dilation experienced by flying in commercial aircraft. The effect is small, nanoseconds over the course of a flight, but it's there. You age slightly less during a flight than you would if you stayed on the ground. This means that frequent flyers are literally time travelers. They're accumulating small amounts of time travel with every trip. Over a lifetime of flying, a frequent traveler might be a few microseconds younger than they would have been if they had stayed on the ground. It's not much, but it's real, it's measurable, and it's happening. But here's the truly unsettling part. If you can travel to the future by moving fast or by being in a weaker gravitational field, then the future you're traveling to already exists in some sense. The block universe interpretation of relativity suggests that all moments in time, past, present, and future, exist equally. They're all real. They're all there in the four-dimensional structure of space-time. When you travel to the future through time dilation, you're not creating that future. You're not determining what will happen. You're simply taking a different path through a pre-existing space-time structure to reach a future that was always there. The future exists now. It's as real as the present moment you're experiencing. This has profound implications for free will and determinism. If the future already exists, if it's already there in the structure of space-time, then in what sense can we say that our choices determine what happens? Are we creating the future through our actions, simply following predetermined paths through a static four-dimensional block? Different interpretations of physics give different answers to this question, but the fact that we have to ask it at all shows how time travel, even the mundane time travel happening all around us, forces us to confront fundamental questions about the nature of reality. Now let me tell you about the most exotic form of time travel that might be occurring right now, involving quantum mechanics. Quantum tunneling is a phenomenon where particles can pass through energy barriers that, according to classical physics, they shouldn't be able to cross. The particle doesn't have enough energy to go over the barrier, but quantum mechanics allows it to tunnel through. But here's the strange part. Some interpretations of quantum tunneling suggest that it happens instantaneously, or even that it might involve negative transit times. The particle appears to arrive on the other side of the barrier before it entered the barrier. This has been observed in carefully controlled experiments with photons tunneling through frustrated total internal reflection barriers. If these interpretations are correct, then quantum tunneling might involve a form of time travel. Particles might be taking shortcuts through time as well as space. Every quantum tunneling event, which happens countless times per second in electronic devices all around you, might involve microscopic amounts of time travel. This is highly speculative. The interpretation of these experiments is controversial, and there are alternative explanations that don't involve time travel. But the fact that we're even considering such possibilities shows how quantum mechanics and relativity together create a picture of reality that's far stranger than our everyday experience suggests. Here's another disturbing possibility. Quantum entanglement creates instantaneous correlations between particles separated by arbitrary distances. When you measure the spin of one entangled particle, you instantly know the spin of its partner, no matter how far away it is. This happens faster than light could travel between the particles. Einstein called this spooky action at a distance, and thought it proved that quantum mechanics was incomplete. But experiments have confirmed that the correlations are real. They're instantaneous. And they can't be explained by any classical mechanism involving information traveling from one particle to the other. Some interpretations of quantum mechanics suggest that these correlations might involve a form of time travel. The measurement of one particle might be sending information backward in time to the point where the entangled pair was created, and then forward in time to the other particle. The information doesn't travel faster than light through space. Instead, it takes a detour through time. Again, this is speculative, but it shows how our best theories of physics lead us to consider possibilities like science fiction. The universe might be full of information traveling through time, creating the correlations we observe in quantum entanglement experiments. Let me bring this back to something concrete. Every hospital in the world uses devices that depend on time travel effects. Machines use powerful magnetic fields to align atomic nuclei in your body. The physics of how these nuclei respond to magnetic fields and radio waves depends on relativistic effects, including time dilation. Particle accelerators used for cancer treatment accelerate particles to speeds where time dilation becomes significant. The particles live longer than they would at rest, allowing them to reach their targets before decaying. Without time travel effects, these medical treatments wouldn't work. So time travel isn't just a theoretical curiosity. It's not just something that happens to GPS satellites and cosmic ray particles. It's part of the technology that keeps you alive. Every time you get an MRI, every time someone receives radiation therapy for cancer, time travel effects are involved in making the treatment work. But here's what really keeps me awake at night. If time travel is so common, if it's built into the basic structure of the universe, then why don't we see time travelers from the future? If it's possible to travel through time, where are the tourists from 2500 AD? There are several possible answers, and none of them are comforting. Maybe time travel to the past is impossible, despite what general relativity seems to allow. Maybe there are quantum effects or other physical principles that prevent closed time-like curves from forming. Maybe time travel to the past is possible, but it requires technologies or energies that are never developed. Maybe every civilization that becomes advanced enough to build time machines also becomes advanced enough to destroy itself first. Maybe time travel to the past is possible, and time travelers from the future are already here, but they're careful not to reveal themselves. Maybe there's a temporal prime directive that prevents interference with past events. Or maybe, and this is the most disturbing possibility, time travel to the past is possible, and people from the future do travel to our time, but they can't change anything. Maybe the past is fixed, not because it's impossible to travel to it, but because any attempt to change it fails. Maybe the universe is self-consistent in a way that prevents paradoxes, not by preventing time travel, but by ensuring that time travelers can never actually alter the course of events. In this scenario, every event that has ever happened, including the actions of time travelers, has always been part of history. The time travelers don't change the past because their actions were always part of the past. They create the events they thought they were trying to prevent. This is called the Novikov self-consistency principle, after the Russian physicist Igor Novikov. It suggests that the universe has a built-in error correction mechanism that prevents paradoxes by ensuring that all time travel is self-consistent. You can travel to the past, but you can't change it because your actions were always part of what happened. If this is true, then free will becomes even more problematic. Are we making choices, simply playing out predetermined roles in a cosmic drama where even time travel can't change the script? I don't have answers to these questions. After 50 years of thinking about physics, I've learned that the universe is stranger and more subtle than human intuition can grasp. What I can tell you is that time travel is real, it's happening all around you, and it's much more fundamental to the nature of reality than most people realize. The GPS in your phone works because engineers understand time travel. The particles in cosmic rays reach Earth's surface because time moves differently for objects at different speeds. Medical devices save lives because doctors can manipulate time dilation effects at the atomic level. Time is not what you think it is. It's not a river flowing from past to future. It's not a universal constant ticking away at the same rate everywhere. Time is flexible, relative, and strange. And time travel isn't some exotic phenomenon from science fiction. It's as fundamental to the universe as gravity, electromagnetism, and the strong nuclear force. You are a time traveler. You're moving through time right now at 1 second per second. Isn't fixed. It can change. It does change. And understanding how and why it changes might be the key to understanding the deepest mysteries of physics and the nature of reality itself. So the next time someone tells you that time travel is impossible, remember the GPS satellites overhead, the cosmic ray particles showering down from space, and the quantum tunneling events happening in the electronic devices around you. Time travel isn't coming someday. It's already here. It's happening now. And you're part of it whether you realize it or not. The universe is a time machine, and we're all passengers on a journey through space-time that's far stranger and more wonderful than our ancestors could have imagined. The question isn't whether time travel is possible. The question is what we do with that knowledge and whether we can learn to navigate through time as skillfully as we've learned to navigate through space. Time will tell. But then again, time isn't what you think it is either.